Welcome to video number 4 of a series of short lectures entitled The End of the Calories In, Calories Out Theory. My name is Francisco Arencibia-Albite. I am an associate professor of Human Physiology at the Universidad del Sagrado Corazón in San Juan, Puerto Rico. The present lecture has three specific aims. First, to derive the equations governing the coincidence of energy balance and weight stability. Second, to demonstrate that the fluctuations of body composition at the coincidence of energy balance and weight stability are dependent on the average VO2 deviation. And finally, to formulate the protein balance equation. As we will see in the final lecture, these ideas set the stage to explore the consistency of the calories in, calories out theory. The concepts and results discussed in this lecture are original and were published in August 2022 in the Journal of Theoretical Biology, and the article is of open access. You are now looking at a macronutrient mass flux diagram. Circles represents macronutrient body reserves. F is fat, C is carbohydrate, and P is protein. G and G stands for gluconeogenesis, and DNL for de novo lipogenesis. The Greek letter alpha is the fraction of gluconeogenesis given by amino acids, and 1 minus alpha is the fraction given by the glycerol released from fat lipolysis. Fi is the average absorbed fat intake, Ci is the average absorbed carbohydrate intake, Pi is the average absorbed protein intake. Fox is the average fat oxidation, COX is the average carbohydrate oxidation, and finally, POX is the average protein oxidation. The macronutrient mass flux diagram can be converted into a more revealing and simpler diagram, as explained next. First, redraw each macronutrient compartment with its corresponding intake component. Second, assign to each compartment a single downward arrow. Now, each downward arrow represents a net outward flux. That is, the arrow represents the sum of the remaining fluxes of the respective compartment, where a flux is taken as positive if it's going away from the compartment, or negative if it's going into the compartment. For example, observe that in the fat compartment, FOX and 1 minus alpha times G and G are positive since these fluxes are outward, while DNL is negative since it is inward. Hence, the net outgoing flux for the fat compartment is given by the following arithmetic operation. In indirect calorimetry, this number is referred as the net fat oxidation. Repeating the process for the remaining compartments produces the net carbohydrate oxidation and the net protein oxidation. From now on, I will refer to this final diagram as the intake net oxidation diagram. Notice that this diagram is more explicit than the original in the sense that it clearly illustrates that the size of each macronutrient compartment is ultimately determined by the balance between the average absorbed nutrient intake and the average net nutrient oxidation. At last, observe that in both diagrams, the calories in is calculated by the next expression, where the Greek letter rho is the energy density of the respective macronutrient in kcals per unit of mass. Calories out, on the other hand, need to account for the change in the size of each compartment. Thus, the calories out must be calculated using the net oxidation terms as shown. The raw oxidation terms in the original diagram should not be used since they do not provide a complete account for the compartment size change. I now use the intake net oxidation diagram to deduce a set of equations based on the calories in, calories out theory. These equations compute the net oxidation of each macronutrient at the coincidence of energy balance and weight stability. First, observe that the diagram implies that at weight stability, the average absorbed total macronutrient intake must be equal to the total net macronutrient oxidation. Otherwise, weight is increasing if the average absorbed mass is greater than the average net oxidized mass, or decreasing if the average absorbed mass is less than the average net oxidized mass. According to the calories in, calories out theory, such state of mass balance must coincide with the state of energy balance, and so the outgoing calories must be equal to the incoming calories. Finally, according to the principles of indirect calorimetry, the total net oxidized mass must explain the daily O2 volume uptake, which justifies the next expression where each K is a constant that provides the O2 volume required per unit of net oxidized mass. In this set of equations, the net oxidation terms are unknown quantities, while the right-hand side terms are known quantities, since we can measure them directly. In order to find these unknown terms, we must proceed as we did in high school when we learned to solve a 3x3 system of linear equations, as the one shown. The next slide shows the solution of the formulated system, and in Lecture 5, I will provide a detailed stepwise deduction of the system solution. As we will see, the VO2 deviation that was introduced in the first lecture is an important component of the solution. This slide shows the solution of the previous formulated system in abstract format. Note that the solution asserts, in accordance with the calories in, calories out theory, that at the coincidence of energy balance and weight stability, the net oxidation of each macronutrient is exactly determined by its absorbed intake and the VO2 deviation, where recall that VO2 asterisk is the O2 volume required to completely oxidize the total absorbed macronutrient intake. To use these expressions for computation, we can apply the following values to the constants in the equations, which results in the next set of ready-to-use formulas. In the next 3 slides, these formulas are applied to a hypothetical weight-stable subject under the 3 possible types of energy balance. That is, under type 1 energy balance, where the average VO2 deviation is negative, under type 2 energy balance, where the average VO2 deviation is 0, and under type 3 energy balance, where the average VO2 deviation is positive. I have placed in the video description a link to a spreadsheet file that implements these formulas to help the audience better appreciate what these formulas are doing. Consider a hypothetical weight-stable subject that on average absorbs 90 grams of fat, 250 grams of carbohydrate, and 110 grams of protein. The total absorbed mass is therefore 450 grams, while the corresponding calories are 2,413 calories computed according to the shown formula. The VO2 asterisk, which again is the O2 volume required to completely oxidize the total absorbed mass, is about 502.5 liters and was calculated with the shown formula. The subject's mean VO2 is taken to be 492 liters per day. Hence, the subject is under type 1 energy balance since the average VO2 deviation is negative with a value of about minus 10.5 liters. As this subject is weight stable, the average absorbed energy must be equal to the average expended energy, and the average total absorbed mass must be equal to the average total net oxidized mass. Thus, if the derived formulas are consistent with the calories in, calories out theory, then their application to the latter data should lead exactly to such outcome. I invite the audience to verify that if this data is fed into these equations, we indeed obtain the balance of energy and mass as shown in the following table. The data in this slide is the same as before, but now the subject is under type 2 energy balance since its mean VO2 is exactly equal to the mean VO2 asterisk. Inspection of the equations immediately shows that the average VO2 deviation vanishes, making the average net oxidized mass of each macronutrient exactly equal to its average absorbed mass. Hence, energy and mass are also balanced in this case. The data in this slide is still the same as before, but now the subject is under type 3 energy balance, since its average VO2 is greater than the average VO2 asterisk. Again, if this data is fed into the equations, we obtain the balance of energy and mass as shown in the next table. I hope this and the previous two examples help the audience to better understand what the derived formulas are doing. But to be explicit, these formulas translate the calories in, calories out theory into the language of mathematics so that its consistency can be numerically tested, as I will do in the final lecture. I now demonstrate that body composition at weight stability fluctuates as a function of the average VO2 deviation. According to the calories in, calories out theory, daily changes in fat mass result from the difference between the daily net fat oxidation and the daily fat absorption, as indicated by the fat compartment of the intake net oxidation diagram as shown. Thus, the average fat mass change must be equal to the difference between the mean daily fat intake absorption and the mean daily net fat oxidation. Now recall that at the coincidence of energy balance and weight stability, the average net fat oxidation is related to the average fat absorption by the following formula. The substitution of this equation into the average fat mass change formula leads to the following result. Plotting this equation shows that at the coincidence of energy balance and weight stability, the average fat mass change is an increasing linear function of the average VO2 deviation. That is, at the coincidence of energy balance and weight stability, fat mass increases when the VO2 deviation is positive, but decreases when the VO2 deviation is negative. Next, recall that the average body weight change is always equal to the sum of the average fat-free mass change and the average fat mass change. At steady weight, the average weight change is 0, and so we write, thus, at the coincidence of energy balance and weight stability, the average fat-free mass change is equal in magnitude to the average fat mass change, but of opposite direction. Substitution of the average fat mass change formula produces the following result. Plotting this equation shows that at the coincidence of energy balance and weight stability, the average fat-free mass change is a decreasing linear function of the average VO2 deviation. That is, at the coincidence of energy balance and weight stability, fat-free mass decreases when the VO2 deviation is positive, but increases when the VO2 deviation is negative. As a result of the preceding analysis, we can conclude that according to the calories in, calories out theory, during weight stability periods, the fluctuations in body composition are a function of the average VO2 deviation. The shown diagram represents the total body protein. Protein enters the body through the absorption of protein intake and is lost through two routes: the net daily protein oxidation and the daily obligatory protein loss, where the latter decomposes into protein loss in feces (PLF) and miscellaneous protein loss (MPL), which includes losses in sweat, saliva, sebum, desquamation, hair, and nails. Under a protein-free diet, the average fecal and miscellaneous nutrient losses are near 12 milligrams per kilogram of body mass per day and 8 milligrams per kilogram of body mass per day, where this data was taken from the work of Tomé and Boss in 2000. As a typical protein contains about 1 gram of nitrogen per 6.25 grams of protein, it follows that PLF is about 75 milligrams per kilogram of body mass per day and MPL is about 50 milligrams per kilogram of body mass per day. Thus, the obligatory protein loss adds to about 125 milligrams per kilogram of body mass per day, which simply means that we can approximate the obligatory loss by the following formula. For instance, the formula indicates that a subject of 100 kilograms will be experiencing an obligatory loss of about 12.5 grams of protein per day. Consequently, to compute the daily protein balance, we can employ the next formula. To conclude the presentation, I would like to emphasize the key points from all lectures so far. In Lecture 1, we learned that by defining the VO2 deviation, it is possible to divide all cases of energy balance into three mutually exclusive categories: Type 1 energy balance, where the average VO2 deviation is negative; Type 2 energy balance, where the average VO2 deviation is 0; and Type 3 energy balance, where the average VO2 deviation is positive. In Lecture 2, we learn about the body composition equations, which indicate that during prolonged weight stability, body composition is also stable. Consequently, if the calories in are on average equal to the calories out, then fat mass and fat-free mass are both stable. In Lecture 3, we learn that the coexistence of caloric imbalance with a steady mass does not represent a violation to the first law of thermodynamics. Consequently, the finding of caloric imbalance in steady weight populations is not a challenge to the first law of thermodynamics. In the present lecture, we have learned that according to the calories in, calories out theory, the coincidence of energy balance and weight stability obeys the following diagram and set of equations. Also, according to the calories in, calories out theory, during weight stability periods, the fluctuations in body composition are a function of the VO2 deviation. And finally, we have learned that the protein balance obeys the shown expression. As we will see in the final lecture, the analytical application of all these important facts will render the calories in, calories out theory as an impossible paradigm. Thanks for watching, and I see you in the next lecture.